So, good afternoon, everyone, and welcome to this LCRIG webinar in association with Gaist. I'm Adrian Tatum, Director of Boundary Marketing and Highways News. The title of today's webinar is Artificial Intelligence or Magic? You decide. AI is everywhere, and so is the hype surrounding the purportedly magical capabilities. AI will be behind an ever-increasing range of developing technologies, and it is already in the highway sector. It's therefore important to know how to determine good AI over bad AI. Gaist have been working with data intelligence in many ways over 17 years, and has developed incredibly powerful AI technology. Its AI technology has been used for several years to develop groundbreaking insight used by many organizations, including national reports for the DFT. The kind of insights delivered by national scale projects such as these simply would not be possible without machine learning. This insightful webinar will equip you guys with a much deeper understanding of what artificial intelligence really is capable of, alongside the limitations and legal issues surrounding this new technology. And at the end of the webinar, you hopefully will be empowered with a better understanding of what is meant by AI, how machines learn, and what questions to ask of AI technology vendors. AI can also drive cost savings, efficiency, and develop new capabilities. But can we trust it 100%? And if not, should we? There'll be a chance for me to read out all of your questions at the end of the two speakers we have today. So please send as many as you can, and I'll try and get through as many as possible. So let's get started. Our first speaker is Steve Birtle. He's Chief Executive Officer of Gaist and founder. Steve, over to you when you're ready.
Thank you very much, Adrian. Can I just check you can hear me okay?
Yes, we can.
Thank you very much. Well, good afternoon, everybody. And thanks for giving up your time just to listen to us. Artificial intelligence, it's a subject that's obviously quite a broad church, and hopefully as we go through this, we'll really try and just lift the bonnet a bit on how AI works, etc. So Gaist, who are we? We've been around, as Adrian said, we've been around for the best part of 17 years now, and we're about making decisions from data. You can see the mission there. So why do we need to talk about AI? Well, it's because AI, one day, it will take control of all technology and it will enslave us all, and there is absolutely nothing we can do about it. So if that's not reason enough, what is? So AI is basically going to tie us all up in knots, and take over the world. Well, at least that's what the film industry would like us to believe. So since the 1950s, we've been seeing movies, stories around killer robots taking over the earth. Obviously, more recently, that's come under the banner of AI, and we've seen a number of movies coming out there where we see the rise of very intelligent robots. Robots that well, beautiful looking robots for one thing, but ones that are exploring human emotion and becoming very, very lifelike. And even as far back as 1968, Stanley Kubrick, if anybody's watched the movie, never forget the sort of very polite but sinister voice of Hal with his interactions with Dave. So we've had this, if you like, this fed down us throat for quite a while now. And if you go on to Google and do a search of the word AI and look at some of the imagery, you can see there's a lot of very emotive imagery around this as well. So we've been bombarded by this view of AI. And I personally believe that the word AI has been done to death, frankly. It's been used so much that it's almost, not to say it's meaningless, but the meaning has been stretched that far that we could almost remove the word AI and replace it with the word magic. It's creating quite a lot of misconception. So what actually is AI, and what does AI mean? And I think personally, to go back to the definition, I think we should go back to where that definition came from. And Professor John McCarthy, back in 1955, he put forward this supposition that every aspect of learning or any other feature of intelligence can in principle be so precisely described such that a machine can be made to simulate it. Now, he went on to add that AI is a machine that has the capacity to solve problems usually done by humans with natural intelligence, and will be considered to have a form of intelligence when it improves itself in performing these tasks. And I think the key word there is improving itself. So that's the definition that AI was born from, if you like. And AI is considered to have a number of attributes, and there they are there. I'll quickly go through them. Simulating the higher functions of the human brain, programming AI to use general language, being able to speak like us, hypothetical neural networks used to perform concepts, so conceptualization of things, measuring problem complexity, self-improvement, I think that'll keep coming up, and abstractions, dealing with ideas rather than events, and randomness and creativity, and that's quite current these days as well. So how many of these attributes do you think we've actually achieved so far today? Well, a surprisingly few, really. The ones that stick out that we've made some progress on is programming AI to use general language. You probably see that all the time now. AI is in there talking to us, chat bots, this kind of thing, where it's trying to communicate with us in the way that we would communicate with each other. Measuring problem complexity, self-improvement to some degree, I would argue, and randomness and creativity. You'll see some examples going through of that. Now, AI can be put into two different types, really: weak AI and strong AI. Now, weak AI is often called narrow AI. Strong AI is sometimes called general AI. So what's the difference? Well, weak AI is AI that can outperform humans on specific tasks it's designed to do. But it operates under far more constraint than the most basic human intelligence. So it can do simple tasks, but in a very powerful way, much more, in some ways, quicker and faster than we can. Strong AI, on the other hand, I think can simply be put as it's AI that's capable of thinking and learning like humans do. So something that's very similar to us in terms of the way that we learn, etc., and we can express ourselves. So and also there is a number of strands of AI that come under the umbrella of artificial intelligence: machine learning, computer vision, natural language processing, robotics, image recognition, knowledge management. These are all forms of AI, if you like, or different types of AI. Now, here at Gaist, we have been working with machine learning for quite some time now, and Stephen's going to talk about that in a little while. So let's just touch on that process. What does that actually mean? Well, if you just go through how we do things. So first thing we do is we go out and we collect very high definition images. We've got some very high-end technology that we use to do that. We go out there, take pictures, essentially, and we use those pictures to teach our algorithms. So we mark them up, we describe what they are, and we feed them to an algorithm. The algorithm then goes out and it detects, locates, and it categorizes features within that image. And then we take that, we report it to our clients, we put it into a form that they can understand, display it to them, and we also do consultancy with them. So we take that data on quite a long journey, really, and the end game being that our clients can use the insight that we derive from that to be able to do their day job, to be able to go out there and put the maintenance that's needed into the network. Now, obviously, it's more complex than that. We do just a lot more than just take a few pictures. And when we fit that together into a whole range of different services that we supply out to our customers, local authorities, government, etc. So we've developed an entire business around managing data and managing insight. So let's just touch on how much of AI do we use. We'd say that we use AI. So how much of it do we actually touch on? Programming AI to use general language. We don't do that. It's not really a part of what we do at the moment. So that's out. Measuring problem complexity. Yes, we do. And self-improvement to some degree, and I'll touch on that as we go through. Randomness and creativity, we don't really use that in what we do. Some of the errors that we get are quite random, but it's not really creative. So we only really touch upon a few aspects of AI. But people will say, well, hang on a minute, Steve, you've got lots of squares over pictures. That's pretty new and exciting. Well, is it? Back 20 odd years ago, we put cameras on a train. I was tasked to survey every track in Britain with a special train, you can see there. And using analog cameras, digital cameras were only just coming in at that point. And we went out there, we collected a lot of imagery, and we were able to detect features within that image and start to do analysis on that in an automated way. So that was very early machine vision. So some of the strands of AI were being done 20 years ago. And image recognition was used in manufacturing probably another 10, 20 years before that. So a lot of this technology has been in the offing for a long time. AI is not necessarily new. Certain aspects of it are, but the component parts have been forming over years. So, we describe ourselves as using artificial intelligence. So let's just remind ourselves what that means. It's a machine that has the capacity to solve problems, similar to that of natural intelligence, and improving itself. Well, that's, you could say that we do bits of that, but it's not fully what we do. But let's look at the definition for big data. Now, big data, and you will have heard all big data mentioned many, many times before. It's a well-used semantic. So big data is a combination of structured, semi-structured, and unstructured data collected by organizations that can be mined for information and used in machine learning projects, predictive modeling, and other advanced analytic applications. Well, that really describes what we do. And I think I wanted to just sort of mention that because there's lots of labels for things in computing these days, like big data, like artificial intelligence, and there's lots of gray areas there. There's lots of overlapping between these semantics. So it's very misleading to describe something as just AI or big data. There's a mixture of all of that in there. So let's talk about machines that improve themselves, because I think for me that's what AI is really. When we really get to the point of having machines that can improve themselves, learn like we can learn, then we get into a place where machines really do have intelligence, and the difference between knowledge and intelligence as well. And I think that's a little cartoon there says it all. We can push lots of knowledge into machines now, but does that actually mean that we're getting knowledge out? So is an intelligent way to get knowledge in leading to an intelligent intelligence coming out? Now, I, for one, and we, as we operate in this field, would argue that it's not really. Intelligence isn't coming out from pushing knowledge in an intelligent way. Intelligence is a very difficult thing to describe, but I don't think we get an intelligent output yet. In some ways we are, but mostly we're not. So what's missing? And it's, in my view, it's reasoning. Being able to reason is a very powerful attribute that machines do not possess yet. So what do we mean by reasoning? Now, here's a good example. Here's some AI that's going to recognize the cow and decided that it's 5.2 meters long. It doesn't take a lot of reasoning to work out that's two cows. But and somebody spent a lot of time there trying to train an algorithm to recognize a cow. But when the algorithm comes across something unexpected, it comes up with a result that's obviously nonsensical, a bit simplest, almost childlike. So it doesn't necessarily mean that you get very intelligent answers from these machines. Now, let's just put intelligence into the driving seat literally here. I mean, we talk about driverless cars and they use AI, obviously, to do their thing. That road that you can see in that image there, both a human and a fully autonomous vehicle will be able to navigate that probably without any problems. The car that's automated will be able to find its way around there. It would sense its way around that bend. Would it do it in quite the same way as we would? Would it anticipate the same things that we would anticipate? I would suppose it wouldn't really. We would drive around that road in a different way. Similarly, when we get to this environment, now this is where things start to get a bit difficult for AI. I mean, you imagine all the different implications there, all the different variables at that junction, many, 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 many times more than you would be on that last picture. So trying to navigate through that as a machine is actually quite difficult. We as humans use, I would say, intuition. We built up knowledge from walking down footways, from being in those crowds, from being in cars, from being in similar situations. We build an intuition that machines can't emulate yet. And that's where we start to see the big differences between human intelligence and machine intelligence starting to open up. You don't need to take my word for it. There's a statement from Matthew Avery at Fatcham Research there. While 80% of self-driving is relatively simple, making the car follow the line of a road, stick to a certain side and avoid crashings like in that image, that's quite simple. But the next 10% involves more difficult situations such as roundabouts and complex junctions. And then the last 10% is really difficult. So it's the 80-20 again. 80% of it is pretty easy. The other 20% takes a lot of the effort and is very, very difficult to overcome. So you can see why there. I mean, if you try and put a driverless car through that environment, what on earth would we get out the other end? We still live in a very complex world, and complexity is something that we are very, very good at dealing with. Machines less so, particularly on the fly and in that way. And we've been doing it. Children can drive cars, and they can drive them very fast. They can drive in very complex ways. So even a child can do much better than AI currently. And but there are cars, autonomous vehicles and semi-autonomous vehicles on the network. And if you ever watch how they drive, navigate themselves around, they do it in quite a childlike way. The capabilities are very childlike. You can teach a young toddler to navigate around a garden and stop when somebody steps out in front of them. And that's similar. The capabilities is now in the car. So we're still at a very childlike state, although those vehicles are very, very complex and very safe, I hasten to add. So where does AI really excel? Well, I would say that completing large, complex tasks in a practical length of time and at a cost that we can afford. That's where we're really seeing the capabilities of AI coming through now. It's given us that step-changing capability and importantly, the capacity to do something. Now, we've seen this before. I mean, humans have been there a lot. The AI is not the first thing to give us a step-changing capability. Once upon a time, somebody fashioned a piece of flint, stuck a shaft on there and created a tool with a bit more leverage, a bit more ability to maneuver it. And they could clear forests, make farmland, and it took them a long time, but they could do that. And that was the start of humans evolving into the kind of societies, etc., that we've got now. Now, of course, we've got much heavier machinery that can do all of that very, very quickly. We've come a long way, of course. But we still need humans to bring all that together. If we chop a forest down and we want to make it into log cabins, there's a different level of complexity involved there. It's not just about knocking things down anymore. It's about being able to fit things together in a very complex way. Humans are very good at that. And that, incidentally, that image was generated by AI. So there's an example of creativity for you. I just dialed that into a piece of software and out came that image. So AI, it can do most things. And I think what it's about really, if you look at take the heavy lift analogy, it's like in that picture there, we've got lots of tools to do the heavy lift, but they're all slightly different. They all do different things. They're all very good at moving different things around for us or flattening things out for us. And that's why I think the algorithms that use AI are like lots of tools in the tool bag. Now, those tools, as capable as they are, they can do that heavy lift, but they create as another problem, I think. If you go back a while ago when we started to decode the genome, that was, I guess, an analogy would be like looking for a needle in a haystack, and it took a long time. But we've developed computing now and AI, not just AI, but computing in general, and the power of processing. But that's created something else now. It's created a haystack of needles. We can very quickly end up with a lot of information, a lot of data. But we still need to find that insight. We need to be able to drill down into that and do something with it. So why all the hype? Where is all of this hype coming from? Why are we hyping it up? Because we didn't used to do that before. Why is the word AI suddenly led to all of this hype? Well, that's because there's an arms race going on. There's a vast amount of organizations now trying to create ever more complex AI and do ever more number of tasks with AI. And what they're seeking, I think, is this holy grail of digital disruption. So, and what do we mean by digital disruption? Disruptive innovation is innovation that creates a new market and value network or enters at the bottom of an existing market and eventually displaces established market-leading firms, products, and alliances. Who wouldn't want to do that if you're in business? To create a whole new market and be the first in there. So that's why there's a vast amount of money being spent on developing AI technology. And in 2021, $93 billion spent on that. $93 billion. We talk about our national debt now being at $45 billion. And we sunk that into just research and development around AI. The previous year to that was about 80 odd million. And this year they're estimating about 150 billion. So, we're seeing a massive increase in funding. And that's leading to a massive increase in marketing and the kind of hyping up of the technology, because people want to be heard amongst the crowd of other technologies, which leads to in some ways, there's a bit of the emperor's new clothes going on. There's a lot of statements being made and people aren't questioning them. And it was interesting. I was talking to an investor that invests heavily into companies. They're a very big investor. I know them quite well. And one of the statements that they made to me the other day was that the majority of claims around AI made by the companies that they invest into are rarely delivered. So there's a lot of talk and not quite just as much output coming out. The success is a lot less than people think. AI is still quite a difficult technology to work with, and depending on how you use it. So AI has brought capability and it's brought capacity but it's how we use it, how we apply it that brings the utility. So at this point, I'd like to hand you over to back to Adrian, who'll introduce Stephen. Thank you.
Thank you, Steve. That was very insightful. Now, yes, as Steve said, Dr. Stephen Remda, who's Chief Technology Officer at Gaist, will give us some further insight following on from what Steve's just given us. So, Stephen, when you're ready, please.
Thanks, Adrian. So, my name is Stephen Remda. I'm the Chief Technical Officer at Gaist. I'm not a wizard, but I do have over 20 years of experience in the artificial intelligence field, mainly around machine learning. Some of that was academic, but most of it was applied industrial experience. So, as Steve said, AI is everywhere. He's mentioned lots of examples where it's in films and the issues around that. And often the media coverage of AI is all very positive for the reasons Steve's mentioned. But I'd like to just point out some kind of counter examples to those. So we're all used to talking to Google or Alexa or Siri. This is a massive area that's been invested into over the last few years. Amazon just earlier this month announced that they were on target to lose £10 billion this year, and it's been confirmed that a lot of their layoffs are going to be in the Alexa voice technology team because they just haven't realised the potential of Alexa, and some people are saying they've missed the opportunity there. We see AI in support bots, so often you go to a website, click on support, and you'll be greeted with a bot who will try and answer your questions. I don't know about the people on this call, but the first thing I do is click the speak to a human button. Microsoft created a bot for Twitter, which was supposed to learn from the people it interacted with. And after half a day, they had to take it down because it started to become quite racist. And then we all see AI used very well in recommendation systems. So Netflix, Amazon, etc., recommending things that are relevant to you. Amazon created a CV screening AI to help them with their applications, and they trained it on their past data. Their AI became sexist very quickly because a lot of the CVs that had been rejected had the words women's college in it or women's football team. And unfortunately, the data it learned from was biased, and the AI found that was a quick way to screen CVs. And it's winning art competitions. Steve mentioned AI generated art. This image here was entered into an art competition by a guy called Jason Allen, and he won first place. That's created a lot of debate around these kind of processes. Is it art? Is it derivative? Is it creative even? And if you stick with us to the end of this slide, I'll show you a website where you can go yourselves to type in any phrase you want, and the AI will generate an image of that phrase. And you'll see some dotted throughout this presentation as well. But what does AI actually mean for our industry? AI is a massive area, as Steve said, but actually here today and now, we're talking about quite a small area of AI. I've highlighted two here, and they're both under the machine learning. The first one is data modeling. So that's where we're looking at how we can use data to look for insight. So what factors influence the deterioration of roads, or what factors, how can we model the traffic on a road, climate change, that kind of thing. But the area I'm going to focus on today is on image analysis or computer vision. And this is a really small section of this diagram here, which covers a small section out of a massive field. So, as Steve said, artificial intelligence dates back to the 50s, where it was first used for in quite controlled environments, and often AI is used in games to kind of test its ability to solve problems. Famously, in 1997, Deep Blue beat Garry Kasparov at chess, the world champion at that time. And in 2017, AlphaGo beat the world's #1 ranked Go player in the world. So making massive advances in those areas where the environment is very controlled and quite contained. In the 80s is where machine learning really started to boom or flourish. And this was, used to do things like spam filtering, optical character recognition, and lots of advances there. And then deep learning, where the focus and the hype has been around the last few years, really started in 2010. And this builds on quite old technology, artificial neural networks, but it's making them a lot more complex and a lot deeper because we now have the computing power to use those kind of those methods at such a deep level. And it was the games industry that helped with this to some extent, because the technology used to render 3D graphics was then used to train algorithms. So Steve's mentioned already some of the benefits of AI, but understanding large amounts of data is one of the key ones there. We can have AI sift through massive amounts of data and come up with insights and trends that we wouldn't be able to do by hand. It's often cheaper, or it can be done cheaply, much more cheaper than the manual effort. So again, if we had to have a look, have a person go through images and draw boxes around bollards, for example, that's much slower than much more expensive than having a machine do it. But obviously, you've got the cost of training that machine in the first place. And the biggest benefit, I think, is that it's automated and a machine approach. A machine process. So these things can be done on demand and instantly, and not having to wait for a human expert to make a decision. So if you think, for example, about a credit card application, you can get a machine to make a decision on that very quickly and instantly, and you don't have to wait for the underwriter to wake up the following morning and assess your application. But there are some problems with AI. Often it doesn't know what it doesn't know. So you will train it on a large set of data, but when it sees something that it hasn't seen before, it could be quite confident about a decision it's made, but it could be quite wrong on that. And I'll show some examples of that later. It can't ask a friend either. So if we have manual engineers, as for example, assessing an image and trying to understand that image, if they don't know, they can ask their friend, or they can ask their colleague what they think about a particular example, but an AI can't do that. It often doesn't understand context, so it will look at something in isolation and try and solve the problem at hand, but it won't necessarily understand the context of that problem. And a good example is back to the CV screening one, where the AI obviously had no concept of sex, but it did discriminate against that. And then the third one is you need a lot of data to solve these first two problems. To give it that general ability, you need to have data which covers all possible aspects. And sometimes the generation of that data can be quite expensive. So the general AI machine learning process looks a bit like this. The first thing we do is we create our training data, the material that we're going to use to train our AI with, to train our model with. We then use AI to train that model. So that's the AI in this process. The AI is training this model to do a task which we've set for it. We'll then evaluate that model and maybe go back and retrain it if there's some issues. But then once we're happy with that model will then be applied, and that's our tool that we've just created using AI. And we will use that model on new data to create new intelligence. And then often when we have humans then looking at the outputs of that AI, we will then feed that back into the training data and retrain, and we'll have this continuous improvement of our model. So how do we know how good our models are, or how good our AI is? One of the quite poor measures is accuracy. So this basically asks, out of all the tests, how often was it correct? Now you could quite easily create a pothole identification algorithm which was 99% accurate by saying that all images did not contain a pothole. And this is because the 1% that did would be incorrect, but the 99% that didn't would be correct. So that would be where your 99% accuracy would come from. So that's quite a poor measure of how well it's doing. We also have recall, which is good for if you're looking at safety critical applications. So this is, for example, if you were training an AI to identify stop signs, the question that recall would answer would be, what percentage of my stop signs did it actually detect? So that's a really good measure. Another one is precision. So this is how relevant were my results? So out of all the things my AI thought were stop signs, what percentage of them were in fact actually stop signs? Again, the AI generated image on the right here was something like Stop Sign City or something like that. There's an article in Highways magazine last year in June about Surrey, who were generating an AI to identify safety defects. And they managed to achieve a 97%, I think this is a recall, 57% recall. And they were aiming, or they said there was a potential for a 90% match rate, which I think they mean recall here again. And what this actually means, if you think about it, is it's going to miss 1 in 10 defects, which for a safety critical application is quite concerning. It's certainly not something I would feel confident defending, for example, if there was an accident. So the issues around AI are that it's a big black box. We don't really understand how it works internally. Data goes in one side, decisions come out the other side, and it's often quite difficult to understand why. Now, I'll caveat that and say that there is a lot of research into what's called explainable AI, which is helping to understand that to some extent, but that's not often used in our industry at the moment. And we don't know how it's going to react to every situation. If it hasn't seen an example that's similar to what it's looking at, it may have issues. And there's been a lot of research into actually attacking artificial intelligence as well, but this demonstrates that to some extent. So here you can see some images that have been fed to an AI, which has determined what kind of image it is. So the black text here represents what the AI would normally say. And on each of these images, you can see that a small pixel has been changed in each of those images. It just looks like noise. So here on the ship, for example, you can see there's a small pixel there and one on the horse. And what this has done is this has changed the algorithm's understanding of that image, and it's completely misclassified these images. And not only that, it's very confident in its assessment. So here you can see 99.7% confident that the AI thinks that's a car. So with these small changes, which admittedly were designed to disrupt the AI, the variation we see on, for example, images from a vehicle is quite large. AI will learn biases from the data. It's not learning anything it hasn't been shown. It is if there are biases in the data, it will learn them too. And it likes to cheat. AI is trying to solve the task, and if cheating is the way to do that, it will do that. Famous example here is on an image classification algorithm. This is on a massive data set, so millions of images, and it was asked to determine what kind of image it is. And these are some examples of what the AI was actually looking at when it determined it was an image of a fish. And when you look at that, it looks like pictures of fingers. And that's because the training data set had a lot of pictures of fishermen holding up their catches, and they were identified as fish. So finding pictures of fingers against some scales was a good way to identify that that was in fact a picture of a fish. So here are some more examples of machine-generated images of roads with various phrases, so flooded roads, good roads, city roads, that kind of stuff. And after the talk, if you guys want to go to that website there, I'll put it in chat later as well. You can generate your own images of absolutely anything. So what does AI actually look like? This is our object detection model applied to our imagery. And as you can see, it's lots of boxes on images. So we see identifying lots of different objects with various confidences. And those are highlighted on the image for the user to see. But actually, this really isn't useful as an end output. There's lots of more processing needs to be done to this to turn it into usable data. As Steve said, AI is just a tool in our toolbox. So, for example, it doesn't tell you what kind of roadstead it was, or what's on the top of the pole, or what kind of sign it is, or the condition of it. For example, that comes at a later step. Our clients also don't want boxes on images; they want points on a map, and just one for each of the objects as well. So, our second challenge is to actually put these onto a map in the correct position that's sympathetic with the map, and we have a very good process for doing that. We do it with defects as well, but again, this is not going to be used by an engineer to make any decision about what to do with that road. We need to turn that into our condition data, and to do that, we have various processes where we will categorize each type of crack. We will determine length, width, size, severity, etc. And then we put that onto a map as well. But again, this is far too much detail. This is massive amounts of data, and our clients, they want insight. They want to know where they're going to put the schemes in, not necessarily what each individual defect is on the road there. So one really good example of where we've used AI without any human intervention is on the lining project that we did with the Department for Transport. So here we trained a model to be able to detect the condition of lining and lining assets such as text and diagrams. And on the left-hand side here, you can see examples of how of what the training data looks like for the area there. So we have the image on the top, and then underneath it, we have an annotated image, which we've created to teach the AI. So the different shades of purple indicate the different conditions, and the different colors indicate the different types of objects that we want to detect. So we created this model. We trained it on tens of thousands of images, and then we actually assessed about just less than 70,000 miles of road in the UK. This is all from our existing bank of imagery. That was total of 146 million images analysed, and it took our AI less than half a second per image. If you consider how long it would take a human to do that, that would just not be feasible at all. And that created 302 trillion data points. Again, massive amounts of data, which is not really any use to anyone in its raw form. It needs processing into something that's usable. So on the right there, you can see the map of the condition of the lining in England as it was in 2019, I think it was. But actually, the DFT didn't need that level of detail. They wanted to know generally what are the trends throughout the whole of England. And because we had all that data, we could look at it regionally. So we could see, is there a north-south divide, and east-west, for example? Are the more rural counties having issues compared to the built-up ones? And we could look at it by the classification of road as well. So, the data made sense. So we saw more lining on A roads than B roads and C roads, and it was in generally better condition on the A-roads as well. So fantastic use of AI there. And it worked well because we had a massive amount of data to process there. It wouldn't be possible to do it manually. There's no chance that it would just take an inordinate amount of time. And we weren't that concerned about the accuracy of each individual prediction. And we didn't, and the anomalies wouldn't matter too much either. We were interested in the overall trends in different classes and different regions. So having an anomaly on a single image, or even several thousand of images, that's going to be a small amount of variation to our overall trends which we were looking for. And any biases as well in the data would affect the data equally. So our aggregations would all have the same biases in it, so it wouldn't be a large issue. And and we managed to as well use the same AI to run the same analysis 2 years later as well. So we got a second set of analysis for free as part of that piece of work there. So AI has its applications. It's a tool in our toolbox, but for safety critical tasks, we always QC our AI work with humans, and that provides a good feedback loop for our AI as well. So I'll hand you back to Steve now, who will give you the summary.
Sorry, I just unmute myself. Okay, so thank you, Stephen, for that. So I'd just like to just put a few more slides in, really, just to summarize what we've been talking about. So I think it's fair to say, hopefully we've got over that AI is not necessarily an industry or a specific product. Really, it's an enabler, and it's an enabler for many things, many industries, and it's covering all aspects of our lives now. But it is that, it's an enabler. It's that added capability and capacity that we've built for ourselves. And like all things, really, there is a question of quality, and I think Stephen's gone into a few things there. The quality of answers that AI can produce is directly relative to the knowledge that's been given. If we give it poor data to learn on, if we get that wrong, or we put things in that are actually in error or biased in some way, that's going to come through for the day. It's the old adage of garbage in, garbage out. It's still alive and kicking today with AI. And it needs that knowledge. I've heard people make claims that they've got AI, and if you can drive it down the street and it'll learn, but it doesn't learn. We have to give it that knowledge. We have to give it good knowledge to be able to do that. I just mentioned the human biases can easily be introduced into AI, and that learning, and we should always remember this, that learning originates from humans. Anybody who says that that AI is definitive, or it doesn't have the subjectivity of humans is wrong, because that subjectivity is what goes into the AI. So we're still putting human learning in. And sometimes AI can exceed our expectations. We get that here all the time. And we have some real breakthroughs with AI. Don't get me wrong, it can do some fantastic things. And other times, like we showed you that long elongated cow that's 6 meters long, we can get stuff that's nonsensical or unchildlike at best. Really, the AI is at the beginning, so it's probably pushing it to expect too much from it. We do get good results, but often these are quite simplistic and childlike, and it's to be expected. We're at the early stages. And like I mentioned before, the thing that's going to bridge that gap is going to take us towards that stronger AI, where the AI moves more towards how behaving the way that we would as humans is reasoning. And we're a long way off being able to design machines that can reason in some ways, but not in the way that we can. We can't make them intuitive. We can't give them personality, despite what Stanley Kubrick might have said. We can't give machines personality yet. They might emulate personality to some degree, but it's not true. And humans have been evolving for hundreds of billions of years, really, if you want to take it far enough. Machines haven't, and we've still got a long way to go. They're still made from microchips, and it's still digital in terms of the way that it works, and as a consequence, it's not like a human yet. So we should really, I think, if we want to employ AI correctly and to get it to work for us, we really need to understand the problem. What is the problem we're asking it to solve? Because hopefully we've both demonstrated, Stephen and I, that AI is a tool, and you can get lots of different variants of it. So there's lots of different tools, and like any engineering project, we would use different tools for different problems. So really, to be able to employ AI properly, we really should concentrate on what is the problem we're trying to get to solve. We had an example there using white lining. Very, very well-defined problem, easy to understand, easy to apply AI in that context, and we got some great results. And I think that's the secret. Give it the right kind of problem, like decoding the genome, for example. It was a very well-defined project and problem, and we got a very, very powerful output in that case. So the output's not intelligent. I think hopefully we've got that over, and we've shown you lots of examples. It can look very clever and everything else, but it's not intelligent. The intelligence is, if you like, in the back end of how we teach it. We can teach it in an intelligent way, and as I made the point, intelligence in doesn't necessarily mean you're getting intelligence out. And we should measure the capability of AI against the questions, like I said in the previous slide. The ability, how well can it answer the question we've given it? That's how we should measure AI, and let's worry about the question. Let's really worry about that. Now, in the future, failing to use AI might be considered illogical or even negligent. When we've got this capability and we've developed it so that it can do tasks more accurately, faster, cheaper than a human, why wouldn't we do that? Why? As I say, in the future, we might even think it's negligent not to do that, if we can. However, we're not in the future. We're not in a Star Trek world. We're in the real world. And using AI now, where it's much less capable than a human, is, I would argue, also illogical and irresponsible, and in some cases negligent. I mean, that picture says it all. Like Stephen says, we would never have AI run through anything that has a safety connotation to it, if we're looking for potholes, for example, because cyclists, like in that picture, if they go down one like that, they can be very, very seriously injured, if not killed. So how on earth can we, or why should we delegate our responsibility to look for these things to a machine that we know is going to be, at the very best, 70-80% accurate, i.e. 20 to 30% of the things it's missing or incorrect? It would be negligent to do that, and we don't do that. So we have to use AI in a very, very responsible way. And if we do, when we give it the right problems, it's got massive capability. So someday, when we've harnessed not just AI, but other technology and different fuels and everything else that we're striving to get to, someday these new technologies will elevate us to this, technological utopia. We're living cleaner, brighter, safer places. Without a doubt, we will. That's the way things do evolve in the end. So we will bring us many, many benefits as we go forward. But today, hopefully we've just shown you, we are really at the beginning. We have, AI is our equivalent, a digital equivalent of the axe. And we've got a long way to go yet to develop the real heavy lift equipment that will get us to that digital utopia, if you like. So anyway, thank you very much, everybody, for listening to us. I think we're going to go to questions now. So I'll go back over to Adrian. Thank you very much.
Thank you, Steve and Stephen. Some really interesting insight there. A couple of questions from me, unfortunately for you, Steve. So trust comes up a lot in your presentation, right? And people listening will be saying, well, actually, AI has been used successfully in the National Health Service. It's been used in the farming sector to make farmers more efficient, more effective. It's been used in car manufacturing, even as we see at the moment in football, to predict the outcomes of games and to measure performance. People will also be thinking, well, if we can't trust it 100%, why use it at all?
I think AI does have its applications where it works really well. I think the kinds of situations you've talked about there are very, very controlled and very kind of well defined. As Steve said, when we can define our problem really well, that's where it can work. It can work really well as a solution. I think when we're interpreting images of roads where there's so many different variables and so many different variations, we're not at a stage yet where we can leave it to go all by itself and make those safety critical decisions. Now, that doesn't mean it can't be used as part of a solution, and that's where we have employed it at Gaist. We use it where we know it's good, and we support the other areas with human QC. So I think that there is a hybrid approach which can work really well as well.
So your safety view,
if I can just add to that Stephen said there, you're right. There are many applications, and I think we did make the point that actually crunching through large data sets, actually AI works very well in there. And looking for patterns. I think AI is very good at looking for patterns. So in terms of screening, I don't know, mammograms, I know it's used there very successfully because they're looking for very well-defined features in images in that case. So there are some, like we showed white lining, there are projects that well structured, and like I said, if you think about that, if you get the problem defined properly, and you don't make it too vague in terms of what you want it to do, then you get some real success. So, and I think it's like everything, if we build a building, if we don't build it to the right tolerances, the thing will fall down. So I think we've just got to make sure that whatever we give the machine to do, we've defined it properly, we understand the capability, and we recognize the errors that may come through from that as well, because there will be errors somewhere. So it's really, as I say, just if we put in AI to any kind of project together, if you do it properly and you well define what you're trying to do, you will get good success from those projects. If you try and make it do something that it's really on the edges in terms of capability of doing, then you get what you deserve. Frankly, you'll get an output that's probably erroneous in places. However, you can then learn from that, and you can reteach the algorithms, and you can go through an iterative process and eventually improve the quality. But I think we made the point is an hours where, particularly if you're sniffing out potholes, which every single one will be different, the AI isn't at that point where it can deal with the random nature of that kind of data. Your
safety view system, Steve, strikes the perfect balance between the human in the safety inspector and your system. So if the system doesn't spot a critical safety defect, the human will. That seems to be the kind of message here. It's not whether you use AI or not, it's how you use it. Just explain how that balance is struck in the context of that system.
Okay. Well, if you're looking at the safety context we talked about before, for all of the reasons, both from a litigious point of view, just from a safety point of view, if we're being tasked to find a safety defect, we are not going to employ fully an algorithm that may be 70, 80, 90% accurate, 95% accurate. And the reason that we don't do that, like I just mentioned before, is if you imagine the defects that we really want to find, the dangerous ones are the ones we see least. And the things we see least is the things that the AI has had less training data for obvious reasons. So we're going to have it try and sniff out the things it's least capable of sniffing out. So in the safety context, we would put humans through every single inch of that imagery to try and find those defects. Yes, we will then compile more and more data on those hard to find defects, or those random defects, safety defects, call them what you want. So down the line, we'll be able to improve AI. But like I've pointed out, potholes is probably the simplest of ones, because to be fair, they are fairly easy to recognize. But what about the sign that's been like a give way junction sign that's been knocked to the point where you can only see it side on? AI would really struggle with that, whereas a human would get that straight away. That's a really good example of reasoning, is that because we know how these things happen, that it may have been hit by a truck, we've got that inbuilt understanding of the context that a machine doesn't have. So if we've got a sign that it's expecting to be presented to us in that way every time we see it, then suddenly it's side on, you've no chance. Well, you have if you train it on lots of data to find that. So we've got to have all of these different variables trained up inside the machine, whereas a human can spot it in seconds without that, that kind of preparation. So safety inspections is definitely an area where we would use AI with caution, and rarely we don't use it on its own at all. In something more like a condition survey, for example, where the implications of missing something are less of a problem, then we would use it more there. So we use it relative to the risk embedded in that data set. And I would imagine that's the same in healthcare, et cetera, et cetera. I can't imagine that, if you're looking for some kind of very rare cancer, that you would just say, well, the computer says, no, it's not there, you're fine. There would be a lot more investigation that go alongside that, I would have thought.
So many people listening might be asset manager or highways managers wondering, how AI might be able to help them do their job more effectively moving forward. If you could maybe elaborate on that. But also, the second part of the question is, could we use AI for tasks at the moment? One that comes to mind at the moment is reducing carbon from the maintenance process and understanding how we measure that reduction and how that then can be audited, et cetera, et cetera. So have you got some thoughts on how AI might be able to help with current and future problems?
Yeah, and this comes back to the semantics again, where if you remember, I mentioned AI and big data. Well, I think what you've just talked about is a problem that's strained the needles more in the big data side than it is in AI. So there's a couple of things, but climate change, and if you're looking at how we can reduce carbon in the network, the biggest way is to get the most from the maintenance that you're doing already. You can put new materials down, yeah, of course you can, but the best way is to not have to need them in the first place, and that's about being able to manage the network and the whole of life aspect of the network over the long term to minimize or maximize the effect of the maintenance, should I say, and to maintain a performance level you're happy with without that intervention. Now, that's a question of putting investment in at the right time with the right materials, the right part of the network, and you're going to get that from a lot of data. So that's a big data issue. Yes, you could use AI to look for patterns in there, but actually it's more about collecting data from connected cars, the kind of thing we're doing now. We're measuring every single minute from 250,000 cars. We're pulling data in all the time. And we've famously cite that we now have the equivalent, we sample the network equivalent to about 3 million years worth of UK PMS data, because we're sampling all the time from cars digitally, etc. When we're building up a dynamic picture of how things are going. Now that's big data. And once you've compiled all that big data, then you can start to use AI to as I said in the presentation, AI is very good at crunching through big data sets and giving you answers. As long as you get the problem or the questions crafted correctly, you'll get good answers. So I'm sorry that's not an AI specific answer. I think it's more of a big data problem. But using data and data-led decision making. Now, that again comes down to what we're trying to work out. Where's best to get that data from? How do we structure it? How do we analyze it? Again, it's what question are we asking? If we get that right, we can get the answers right, I think.
And I guess what's happening with that data that you're getting from those cars? What's happening with that data at the moment? So you're building a real-time picture of the network. How can we use that type of data to help enhance what we've got already? So how can we translate that back into a scenario where an asset manager has got really accurate data that says, I know this road definitely needs to be surfaced, but this road, we could probably put asphalt preservation on that and it might last for another 8 to 10 years without the expense of resurfacing it. Or look at the joints, so we need some joint sealing there. Could AI help with that?
As part of that, so first of all, AI can help in terms of recognizing the condition. Of course, we're just showing you how we can do that. We run it through, tell if you've got fat in, if you've got deterioration on a joint, as you mentioned. In terms of determining which roads, you asked how connected car data potentially can help you with that. Well, currently, the prescribed wisdom is we go and we measure the network at least once a year. Well, sorry, at least once every 2 years. Most of the clients on the principal roads are doing it about once a year. Some once every 2 years. Now that's giving us an idea of a curve. Now in 10 years, we'll get 10 points on that curve, that deterioration curve. That's not a lot of points to measure a curve. When you put the random factor of traffic in and weather and everything else, connected car data that we're collecting is coming in all of the time. So instead of having 10 points on a curve, we'll have millions, if not billions of points on that curve. So that will allow us, and across all of the network, so that will allow us to see, you're talking about comparing one road with another. One of the things you didn't state is which road is declining fastest. Now we can see which is declining fastest, and we can see which actually got its impairment from weather as opposed to traffic. So that's telling us how much damage weather is doing, and then we can start overlaying weather patterns and climate change. And that, I think, is how big data and AI is really going to start crunching through and giving us some real answers to how we manage a network. We can take it down to street level with AI and start looking at what specific defects are there. And I think that's this tool's in the toolbox. It's like I showed all that heavy lift equipment. There are different elements of technology that, when compiled together, then create a real process that allows you to get some real insight out the other end. And we are only just getting those tools now. Like I talked about digital acts, we are there. We are now getting lots of car data coming in from normal cars. It's coming through the door like an avalanche. So how do we structure it? How do we compile it? How do we analyze it? How do we aggregate it? Those are the things that we get employed to do. That's what we do as a business. What we're trying to find is ever more novel ways of giving really clear, concise insight to our clients, so that with their ever diminishing amount of money, they can either make a case for more money if they're very lucky enough to be able to get that from somebody, be it Treasury, challenge from bid, whoever, or if they can't, to say, well, I've only got so much money. Well, we can tell them where we put that to get the maximum effect for that over the long term, and demonstrate what that will look like in pound, shilling, and pence in terms of a return on that investment. That's the value of the technology that's available now that hasn't been available until very recently.
And do you think that can help take us to another level, Steve? So the challenge we've got at the moment, which the Road Surface Treatments Association is talking about, is striking that balance between reactive and proactive maintenance. And ideally, we probably need to be more in the proactive maintenance than the reactive. So ideally, we want roads where potholes don't form in the first place, right?
Well,
and therefore,
yeah, I think that goes without saying.
We could then present an argument to the DFT that says, actually, we need less money for potholes and more money for surface treatments, because we know those surface treatments are going to keep the roads in better condition for longer. Does what you've just presented? Do you think it helps with that overall objective?
Definitely. If you look in, you've got to look over the whole of life. I mean, we've been talking about whole of life asset management, haven't we, for years and years now. The whole of life asset management, whole of life view on a network is obviously where we should start. But that aligns itself to the political priorities within an organization. There's a number of factors outside of our control, but at the end of the day, we should start to look at the long-term impact of what we're doing now. Now, you're right, and everybody on this call who's involved in the highways industry knows that if you go around fixing potholes, that's not necessarily a very viable long-term solution. Eventually, that's underlying structural defects will get you in the end, and they'll get you in a very aggressive and very expensive way, because if you keep just patching, of course, the underlying structure is going to start to fail. You have to then plane out deeper and deeper and put ever more aggressive treatments in. They're going to cost more money. But if you can model that, if you can show that to the members or whoever, and say, right, we've got options here. We can manage a decline, by the way, and we can keep it safe. But at the end of the day, the children that are running around in the playgrounds at some point are going to have to pay for all this, and they'll pay dearly for that. Or we can start to invest a little bit more now, or even borrow money up front and remove a lot of that not aggressive, but those more structural defects. And that will allow us to spend more on preventative than it will on reactive. And it's all about that balance. And once you've got a view of the network, forensically what you've got there in terms of mode of failure, different material types, volumes, etc., which historical surveys have never given you. We can now give that, but also we can overlay on that the rate of decay, the rate of decline, when the impairment's coming in. we can start now to model what climate is doing to a network. So then you can factor that in, saying, not only do we have to, manage the backlog that's coming through now, we're going to see the weather throwing the kitchen sink at this as well. So we've got to now start to account for that. But we know that this year, in these kind of weather, these kind of conditions, we picked up this amount of impairment. If we're going to get more of this year on year, this is the ever increasing amount of impairment that's going to come from the good old wind, rain, and cold. So again, this is all data. It's all data. It's all there now, and I think we're going to go into a new golden age. I don't like to use that word. But we're going into a new era of extracting the insight out of data. I think big data was talked about, and we've been running around collecting more fancy ways of collecting lots and lots of data, as we are now doing from cars. We have vast amounts of data. I think we're now going to move into a phase where we're going to start to understand it. And I guess I was at a workshop just yesterday with a number of councils looking at barriers to innovation, and I think we were talking about this point of understanding the problem now. Let's form the problem, let's form the questions, and then we can start to plumb this technology in to bring these answers out once and for all.
Okay, so I've got a question here from a member of the audience. I'm not sure whether he wants to mention the council or not, so I will say a council had a condition survey and a lining survey from Gaist from 2021 data. What level of AI was used in these two surveys? He says he presumes lining used more AI than condition survey. How long until condition surveys have more AI involved and less human interaction?
Well, without knowing what it is, I couldn't say exactly what the ratio is, but certainly lining is I'll talk more generally. Lining is something we would do more automated than we would with and there's a reason for that. Again, I think I mentioned it. AI is very good at patterns. And the good thing about lining is it's designed to present itself in exactly the same way all the time. A giveaway line, a white line, broken white line, studs, you name it, cycle symbols. They've all been standardized so that we can understand them. So it makes it easy for a machine to understand. So that works well. And we use, and as Stephen pointed out, we use vast amount of vast amount of data on the national surveys for the DFT. Condition surveys, we've been ramping that up more recently. We double check, and we also attribute with humans, because AI can detect a lot of things without a doubt, okay? But the level of attribution that we want to go down to be able to facilitate the modeling I talked about, etc., we add that in by a human. So the machine does an heavy lift and identifies these features, but we might add that detail in that AI is not very good at. I'll take out the mistakes, like the cow with two cows either side of it. It's now 7 meters long. Those are the kind of random things that come through. We don't want random errors in our data, because if we model that and we've got 10%, let's say we were really good at this and we had AI and it would give us 90% accuracy. We've got 1 in 10, like Stephen said, 1 in 10 things would be wrong. So let's then go and take that and we'll go and model that for 25 years. How big an error am I going to get at the end of that? So we can't afford to have data that is at that 90% accurate, 70%. Some of our competitors are quoting 70% accuracy. That means 30% is wrong. So yes, you can get, if you want an approximation, you can do that straight off the back of AI. If you want to have a vague idea of the state of something. But if we're talking about whole of life asset management, which is what we just discussed, you need down to, really the best data you can get. So we use the combination of the power of a human, which is still very powerful, much more powerful than the machine, but the heavy lift capability of AI, that's a brilliant place to be, because we can cost effectively bring the two things together to get that high order of accuracy. And you're absolutely right. As AI gets better, the needle will shift over and further towards using more of that human, less of the human intervention. We randomly check as opposed to checking everything. And we may be that confident we'll start looking for safety defects with it. But where we are right now, we're probably still at that 80-20 and going, we're making steps forward, but we are using it responsibly.
Okay, thank you very much. Thank you, Steve. I think that's all we've got time for now, folks. So thank you very much for logging in. Thank you to Steve and Stephen. If you want to know more, you can email info@gaist.co.uk to ask any more questions. And I wish you a happy weekend. Thank you very much.
Thank you. Bye-bye.